In the previous video, I introduced the concepts of order of forces and energy. However, that video was missing one thing that is usually introduced early on during physics classes: kinetic energy. In the real world, kinetic energy is 1/2 of mass times velocity squared. To generalize it to different orders, it's useful to introduce new notation first. Quantities with units of distance times time to the minus n are called motions of order n and are written as m subscript n. So distance is a motion of order 0, velocity is a motion of order 1, and acceleration is a motion of order 2. With this, we can write the formula for kinetic energy as kinetic energy of order 2 equals 1/2 times mass times the motion of order 1 squared. We need to generalize the formula so that we can input a motion of any order to get a corresponding kinetic energy. The work of a force should be equal to the change in kinetic energy of the object that the force is applied to. So, to find the formula, we could start from energy of order n is equal to force of order n times distance. We also have a force of order n equals mass times distance times time to the minus n, which is equal to mass times the motion of order n. We can substitute the force formula in the energy formula to get energy of order n equals mass times motion of order n times distance. But here we need the distance to calculate the energy, but it doesn't make sense to have the energy depend on the distance traveled. Thankfully, we can find the distance traveled by integrating the motion of order n times with respect to time. The result of this integral is distance equals 1 over n factorial times motion of order n times time to the n. If we then substitute the result of the integral and the force formula in the energy formula, we get energy of order n equals 1 over n factorial times mass times motion of order n times motion of order n times time to the n. Now, we can combine and distribute the time to the nth term into the motion of order n terms, which gives us energy of order n equals 1 over n factorial times mass times motion of order n divided by 2 squared, which gives the kinetic energy for a motion of order n divided by 2. If we plug 2n into the formula, we get the formula for the kinetic energy of a motion of order n, which is energy of order 2n equals 1 over 2n factorial times mass times motion of order n squared. One thing to note is that even though the formula for kinetic energy comes from energy of order n equals force of order n times distance, the order of the work of the force is different to the kinetic energy, except for forces of order 2, since 2 is the solution to the equation 2n equals n plus 1. And as forces of order 2 are the only forces that exist in the real world. With this, you might think that I made some mistake, or even that this idea of forces of different orders doesn't make sense. But there is actually a simple way to explain why this is the case. Let's think about an object with constant acceleration. For that to be the case, it needs to have a motion force of order 2. It doesn't matter if a force of order 2 is applied on the object, or if it gained that motion from an order 3 force. But I think it's easier to think about an object with an order 2 force applied to it, since now the question is what is the energy needed to keep applying a force on the object. Force is related to power by P equals Fv, so the power depends on the force and the velocity of the object. But since the velocity changes linearly with time, since the object is accelerating, the power needs to change. So the answer needs to have units of power divided by time, which is the energy of order 4. And if we find the kinetic energy for an object with a motion of order 2, we get an energy of order 4. See you in the next video. Goodbye.